Okay, good. So we've got this integral to perform. Well, the first thing to notice is we can take out e to the b squared over 2 alpha. That doesn't depend at all on x. And then we've got an integral from minus infinity to infinity. I'm going to write dx. It really doesn't matter what I call the integration variable. And then I'll get minus alpha 2x squared because I'm now calling x prime x. So that's the integral that I have to do. Now, do you notice anything? Well, yes. This bit over here, that is nothing but I naught. I naught was the integral from minus infinity to infinity dx, e to the minus alpha over 2x squared. And that's exactly what we have sitting there. So this is just e to the b squared over 2 alpha times by 2 pi over alpha square root. And I have just used the value of I naught to get that answer. So what is remarkable is we managed to calculate I of b knowing only the value of I naught. So let's just recap the logic. We wanted to work out In. Instead of working out In, we said, well, let's work out I of b. And the point was that we could get In by taking derivatives of I of b and evaluating things at b is equal to 0. And what we've just learned now is we can actually calculate I of b knowing nothing more than I of naught. So this is exactly the logic that we want to mimic when we want to evaluate the path integral. So let me start sketching out how that argument works. Okay, so I'm going to remind you, this is what we've just evaluated. Okay, so we evaluate an integral from minus infinity to infinity dx e to the minus alpha over 2x squared x to the n. And this is what we called In. That's what we want to calculate. That's our toy model problem, if you like. What's the real problem that we'd like to solve? Well, we want to calculate this correlation function. Okay, so I'm still going to have to prove to you that this really is a correlation function, but this is the basic formula that I've asked you to accept about path integrals. This is given by a path integral over the field phi, e to the is phi of x1 phi of xn. You might call this a definition of this correlation function, and then ultimately what we would love to be able to do is to argue that this correlation function is related to the time-ordered correlation functions that we evaluated so far. But for now, view this as an integral that somehow we want to perform. So what did we do with our toy problem? Well, we said let's introduce a function, I of b, and I of b was defined to be an integral from minus infinity to infinity dx e to the minus alpha over 2x squared plus bx. And what was the important thing about this function IB? Why was it interesting? Well, because if we took derivatives of IB with respect to b, sorry, and evaluated this at b is equal to 0, we got In. So it's this last box formula that I just added. This is the reason why I of b was interesting. Okay. So now let's introduce z of j. What z of j is, it's an integral d phi e to the is plus an integral d4x j of x phi of x. J of x is some arbitrary function. It's much like b in our toy model problem. And b multiplied x, which is our integration variable. Here, j of x multiplies phi of x, and we've integrated d4x. And phi of x is our integration variable. So you really should think about z of j as just like I of b. And why is z of j interesting? Well, z of j is interesting because of the following formula. If we take n functional derivatives of z of j, sorry, let me just do that. So we're going to take n functional derivatives, j1, up to j of xn, and we'll evaluate it at j is equal to 0. It turns out that this is nothing but phi of x1 up to phi of xn. So this last formula that I'm writing down now, this I want to spend a little bit of time proving to you. But if this last formula is correct, and I'm going to try to convince you that it is perfectly correct, then I hope you can see we've perfectly replicated the logic that we've just used to calculate IN, but we're now using it to calculate correlation functions in the part integral. And the nice thing is, you know, we were able to do the calculation of I of B. So let's maybe put that down. We used only the value of I naught. So if you told me the value of I of naught, I was able to calculate I of B, and then all of the INs. Here too, we will see that we'll be able to calculate Z of J, and we will use only Z of naught, which is integral d phi e to the is. Okay, so we're going to get a perfect matching of the logic. Good. Okay, so let's try to prove this formula that I've just put the star in that box. That's maybe the most important formula on this page, and it'll show you that we've perfectly reproduced the logic that we were just using for ordinary one-dimensional integrals. Now, I want to remind you of something. Here's a subtle point. So let's call this comment a comment on functional derivatives. You see, we typically use functional derivatives in two places in field theory, well, at least two places, but we use them slightly differently. So you have already used them in the Hamiltonian formulation. Remember when we were calculating Poisson brackets of the fields? There we did use a functional derivative, but the functional derivative that we use there is we vary on a fixed time slice. So the kinds of things that we did, we want to vary the function phi of t comma x, let's say, with respect to the function phi of t comma y. And here you should really think that phi of t comma x is just some function of x, and we're varying it with respect to some function of y. So this gave us a three-dimensional delta function. And that's what we used in the Hamiltonian formulation. Perfectly good formula. Here we mean something slightly different. Now we are varying, let's say in space-time. You know, I haven't restricted myself to a time slice, so I'm really varying functions that depend on t and x. They're allowed to have a non-trivial variation of t, and I change t when I do the variation. So now if I calculate delta j of x, delta j of y, this will actually be a four-dimensional delta function, okay? So there will be one term which sets the two times equal, and then the term that you're used to, which is just the spatial delta function, okay? And that's because we're now varying functions that depend on four coordinates, whereas in the Hamiltonian approach, we're varying functions that depend on only three coordinates because we've held t fixed. We're only thinking about how things depend on spatial X and spatial Y. So these functional derivatives with respect to J, we're varying the functional dependence both on the space and the time component. Okay, now you've worked a little bit with these functional derivatives, so let's just do a little reminder of the most important points. So probably the most important functional derivative that we'll want to calculate is a delta j of x1 of e to the integral d4x j of x phi of x. Now you should know enough to evaluate that functional derivative. So go ahead, give it a shot, and once you've figured it out, watch the next video. Good.